Hey everyone, we're going to talk about parameterizing surfaces in this section. So up until now, you've seen this word parameterizing a lot. It really just means writing a set of parametric equations to describe something. We've mainly parameterized curves and lines at this point. Now we're going to look at how we can take parametric equations and figure out what surface it makes, or if we can look at a surface and figure out what the parametric equations are. So to start off, we're going to look at an example. Let's say that we have a yeah, let's say that we have a three-dimensional surface that is given to us as a vector valued function in terms of the parameters u and v. Okay, we'll say that we have 3 cosine of u I plus 3 sine of u j plus v k. All right. So when I look at this, the first thing I notice is that I have a sine and a cosine that have the same coefficient, which tells me that there's a circle involved in this somehow. Specifically, very good. All right, specifically, there are circles that are going to be parallel to the xy plane, right? Because the I and the j components make up the circle with a radius of 3. In addition to that, we're also told that u is between 0 and 2 pi, and v is between 0 and 4. Okay, so what this tells me is that I'm doing a full circle, right? 0 to 2 pi. And my z coordinate is ranging from 0 to 4. Basically, I have circles and I have a height. That means that this makes a cylinder. Right, so this is what our surface would look like. Now you might be thinking, well, that looks like it should be the equation for a spiral, and that's right. It is a spiral. Just think about what kind of three-dimensional surface is enclosed within a spiral, right? So if I draw the spiral out, that in the back, that in the back, right? So if I had to draw out the spiral, it would look something like this, kind of wrapping around that cylinder. So when we say parameterizing surfaces, we're looking at what surfaces are enclosed in these space curves that we already know about. Let's look at another example. Let's say that we're given a vector valued function, r of u and v. So u and v, again, are parameters. And this time we'll say that we have sine of u cosine of vi plus sine of u sine of vj plus cosine of u k. Oops, that should be a j, not a k. Yeah, u k. All right. And we're told that u ranges from 0 to pi. And that v ranges from 0 to 2 pi. Okay. So with this information, one thing that you might notice, and it's another thing that you may have even noticed in the last example, is that this almost looks like the Jacobian that we get when we go into spherical coordinates. And you might have noticed that this kind of reminds you of cylindrical coordinates. Cylindrical coordinates, cylinder. Spherical coordinates, this is going to make a sphere. To give you another way to think about that one, I see a bunch of sines and cosines. So I know that if I were to square these terms and add them together, I might find something interesting. So we know that from this vector value function, x can be written as sine of u cosine of v. We know that y can be written as sine of u sine of v. I keep trying to do that. All right. And z can be written as cosine of u. So if I were to write out x squared plus y squared plus z squared, I know that this looks like the left-hand side for the equation of a sphere that is centered at the origin. So if I were to use my parametric equations to simplify this, I would end up getting, I'm going to write parentheses, just square everything. I would end up getting sine squared u cosine squared v plus sine squared u sine squared v plus cosine squared u. And this would be what I get from squaring x, y, and z and adding them together. Now, if I were to look at these first two terms, notice that you have a sine squared u in both of them as a factor. So you can factor out sine squared u, and that's going to leave behind cosine squared v plus sine squared v. And then left over, we have this cosine squared u. So we know that cosine squared v plus sine squared v gives us 1, Pythagorean identity. That's going to leave us with sine squared u plus cosine squared u, which, guess what, is also equal to 1. So by doing that, we've shown that these parametric equations can also be written as x squared plus y squared plus z squared is equal to 1. That gives us the equation of a sphere centered at the origin with a radius of 1, also known as the unit sphere. Another way that you can think about it kind of along the same lines is how I started the cylinder problem. If you look here, there appear to be a couple of circles going on. So I know that I have a circle involving this V in the XY plane, right, with a radius of 1. So that's going to give me this. I know that I have basically a circle that can also be made in the XZ and YZ planes, each with a radius of 1. Right, so altogether that makes a sphere. Okay, so this is kind of just a way for us to look at a set of parametric equations and describe the shape that we see, which really is more of a precursor to what we want to be able to do. So let's look at an example of something that we are going to need for future reference. So in this next example, let's say that we're given an equation in terms of x, y, and z. Right, and we want to write a set of parametric equations. In other words, we want to parameterize, this, whatchamacallit, this surface. So if we, So remember, when we write parametric equations, one of the things that we do is we look for the path of least resistance when writing these. So the easiest thing to do would be for me to let x be one of my parameters, let y be another one of my parameters. Because you saw in those other examples that we're parameterizing using two parameters because it's a surface, right? One parameter will give us a curve. Two parameters will give us a surface. All right, so if that were the case, I would let x be u, I would let y be v. That means that z would be the square root of u squared plus v squared. And that would be a set of parametric equations. Remember, we could also write this as a vector valued function. Those are two different ways to express the same information. So I could write this as a vector valued function r of two variables, right? So I could let r equal ui plus vj plus the square root of u squared plus v squared k. And that would be equivalent. So at this point, we actually parameterized a cone. Full stop. Okay, another thing that we can pretty readily parameterize are something that you looked at back in Cal 1, Cal 2, surfaces of revolution. So for example, if I have the function y equals 1 over x, we know that in the xy plane, we know that in the xy plane, this is going to be that graph here where we had a vertical asymptote along the y-axis. Then there was a graph down here in the third quadrant of the xy plane that basically had similar properties. It's just a reflection, right? So if I wanted to parameterize this function, f of x equals 1 over x, where x is between 1 and 10. First off, that would take off this entire part in the third quadrant. We would only be focusing on this piece. And let's say that I'm parameterizing the solid that we get from revolving this around the y-axis or the x-axis. So in other words, it would be like if I took this whole region here up from x equals 1 to x equals 10, and I just spin it around that x-axis. Basically, I would make these circles all along the x-axis of varying radius, eventually leading me to the shape which you may have heard of called Gabriel's horn, which actually extends out infinitely, right? And kind of goes back to some of the things you learned about improper integrals in Cal 2, right? Which related directly to series, right? But I'm not going to go down that rabbit hole. Right, so anyway, we have this three-dimensional surface, and we can parameterize this surface, meaning write a vector valued function or a set of parametric equations for it, based on the fact that we got it from revolving a one-dimensional or a one-variable function around an axis. Right, so specifically, I know that in the xz plane and the xy plane, or actually, let's think about this. Yeah, parallel to the yz plane, right, we have all of these circles. Right, which means that our y and our z are basically going to be parametric equations that involve circles. The radius of the circle varies depending on what this y value was, right? So if the y value was 1 over x, right, then the radius of the circle would be 1 over x For the y, um, yeah. For the y, just think about, or to figure out which one is the cosine and which one is the sine, I want you to think about how the yz plane looks compared to how the xy plane back in the day looked, right? So this is our horizontal axis, this is our vertical axis, meaning the y is going to be our cosine, and the x is going to be our sine. So we've got our parameters in terms of x and in terms of angle theta, right? If we want to use the same notation that we've used pretty much throughout this, we would let x be equal to u, right? And we would let y be equal to 1 over u times cosine of v. We would let z be 1 over u times sine of v. So at this point, we have the equations. If we wanted to get the values, we know that v would range between 0 and 2 pi because we're going all the way around the circle. And we know that u would range between 1 and 10 because that's how far we're going out on the x-axis. So altogether, we've come up with our parametric equations as well as the bounds on the parameters. Remember, you could also write that as a vector valued function, r of u and v equal to ui plus cosine of v over uj plus sine of v over uk with the same restrictions on the parameters u and v. So u is between 1 and 10, and v is between 0 and 2 pi. So that's an alternative way of writing that same parameterization. All right, so the next thing we're going to look at is normal vectors and tangent planes, which we've talked about a little bit. But we'll kind of do it in a different light now that we have a little more information. So here's the thing. When we parameterize a surface, okay, so if I have some kind of three-dimensional surface, I'll draw what, you know what, I think I will draw a plankton. I've talked about that one in a while. All right, and in your own notes, if you would like, you can make it into a plankton. All right. But anyway, let's say that we have a surface that looks like this, okay? If I pick any point on this surface, and I've parameterized the surface in terms of u and v, when I get my tangent vectors, right, I can get tangent vectors in terms of u. I can get tangent vectors in terms of v. So remember, your plane will contain both of those tangent vectors. And we can actually get the equation for that tangent plane using the vector that is normal to both of them, right? Which we can get by taking the cross product. Right? U cross V, which we've denoted as capital N for normal. All right. So other thing I want to remind you of is, how did we get tangent vectors? How do you get tangent lines? You used a derivative, right? So we can get tangent vectors by taking the derivatives of the parametric equations that we write. The thing is, if we're writing in terms of two variables, we'll need to look at partial differential equation, or no, we'll need to look at partial derivatives of the vector valued functions. So essentially, let's look at an example next. You want, you can draw the chum bucket in the background. All right, so let's say that we have an equation for a paraboloid. All right, so paraboloid, remember that's like our little ghost costume, right? And we are already given our parametric equations for the paraboloid in terms of two parameters u and v. So we would get ui plus vj plus u squared plus v squared k. Right, and we want to write the equation of the plane that's tangent to this paraboloid at the point 1, 2, 5. So this is honestly something that you guys have done before. Like the only difference is now instead of differentiating with respect to just t, you're differentiating with respect to two parameters. And in this case, if I take the derivative of my parameterization with respect to u, right? Derivative of u is 1. So we'd get 1i. There is no u here, so derivative of that would be 0. There is no j component. And then derivative with respect to u, we would get 2u. This would be 0, so plus 2uk. If I were to write the partial derivative of r with respect to my other parameter v, we would not have an I component. Derivative of u with respect to v would be 0. J component would just be 1j. And then k component, we would get 2vk. So now that we have our partial derivatives, we can actually set up the equation or the determinant that we would need to find our normal vector. And remember, y'all, the components for the normal vector are what gives us the slopes for the different parts or the different terms in the equation of the tangent plane. So, yep. All right. So, yeah. Right. RU cross RV, right? Just using the shorthand notation for our partial derivatives is equal to a 3x3 determinant, where the first row is our vectors, our unit vectors ijk. And then we go in order. Second row will be components of derivative with respect to u. So for I, that was 1. For j, that was 0. And for k, that was 2u. Then the third row is going to be the components of the derivative with respect to v. So 0 for the I component, 1 for the j component, and 2v for the k component. Now, when I take my determinant, we have I times the determinant of 0, 1, 2u, 2v, minus j times the determinant of 1, 0, 2u, 2v, plus k times the determinant of 1, 0, 0, 1, also known as a 2x2 identity matrix. All right, and if we were to continue simplifying, I would get I times 0 minus 2u, so negative 2u, minus 2v minus 0, so minus 2vj, and then 1 minus 0, so plus 1k. So altogether we get negative 2ui minus 2vj plus k. So this will be our normal vector basically at any coordinate. right? But keep in mind, this is not in terms of x, y, and z. This is in terms of u and v. So we have to go back and figure out what the values of u and v are at the point that we want. All right, so this is the normal vector at a point uv. If I want to find the normal vector at the coordinate 1, 2, 5, I have to figure out what u is and what v is. Luckily for us, it's pretty straightforward. X is u, so u would be equal to 1. Y is v, so v would be equal to 2. And if I wanted to test that, I know that the z coordinate would be u squared plus v squared. 1 squared plus 2 squared gives me 5. So it lines up. So with that said, we know that we're essentially looking for the normal vector when u is equal to 1 and when v is equal to 2. If I plug those values in, I get -2 for my I component, -4 for my j component, and 1 for my k component. And there we go. That's the normal vector. Now that we have the normal vector and we know the coordinate that we want the tangent plane at, we have everything we need to write the equation for the tangent plane. So remember, your normal vector gives you the coefficients. So we have -2 for the x minus 1, because 1 is the x coordinate. I shouldn't have wrote plus, minus 4 times y minus 2 for the y component. And then for the z component, we have plus 1, so plus z minus 5 equals 0. And that is the equation of the plane. That's a totally acceptable answer. Your textbook goes a little bit further in the example and just distributes and moves things over. They end up getting, what do they get? Let's see, -2x minus 4y plus z equals -5. Yeah. So if you combine like terms and move the constant over, that's what you would get. All right, but both of these are acceptable answers for equation of a plane. All right. So now that we've relearned or reviewed and kind of tacked on a little bit to normal vectors and tangent planes, the last thing that we're going to look at in this section, right, involves finding surface areas, right? So the surface area of a three-dimensional surface can be obtained by doing that. So you remember we parameterized the surface, at least in some regard, using either rectangular or polar coordinates, and then we converted ds to be the arc length dy dx or dx dy. Here, if we are able to parameterize the surface using this two-variable approach that we've got, we can actually write it out as the double integral over some region D, which would be our parameterized space, of the magnitude of basically your cross product that you calculated to get your normal vector. Yeah, dA. Right, so basically this is your normal vector, the magnitude of your normal vector. And if we look at the next example, okay, let's say, or they want us to find the surface area of a unit sphere. And they give us R in terms of the parameters U and V. All right, sine. And we've already actually seen this particular one because that was one of the first ones we looked at. Okay. And we're given bounds for the different parameters. All right. So to find the surface area, essentially we're going to be looking at the double integral. By the way, this is going to describe D because you're given the bounds on the parameters, not on X, Y, and Z. All right, so we need to find what our normal vector is by taking the cross product of the first partial derivatives. And then we need to find its magnitude and set up a double integral. And that's how we find our surface area. So starting off, we know that the cross product, RU cross RV, is going to be a 3 by 3 determinant. First row are the unit vectors I, j, k. Second row, we're going to look at the first derivative with respect to u. So anything involving v, we treat as a constant. Okay, for the I component, I end up getting cosine of u, cosine of v. Definitely might want more space there. I'm gonna make myself more space, y'all. Okay, and then for the j component, yeah, then for our j component, we end up with respect to u, cosine of u, sine of v. Then for our k component, negative sine of u. And then our third row, we're going to take the partial derivative with respect to v. So for the I component, that's negative sine u, sine v. For the j, sine u, cosine v. And for the k component, there is no v, so that would be 0. All right, so to find our normal vector, there it is. All right, so to find our normal vector, we're going to need to compute the cross product for these. And I'm going to tell you right away, it's going to involve trig identities to simplify this as far down as we can. So we have I multiplied by this 2 by 2 determinant. All right, minus j times this 2 by 2 determinant. Plus k times this 2 by 2 determinant. All right. So expanding, we're going to get 0 minus negative, so plus sine squared u cosine v. For our j component, 0 minus positive sine squared u sine v. All right, and then for k, we'll have sine u cosine u times cosine squared v minus a negative, so that'll be plus sine u cosine u times sine squared v. All right. So looking through these, looking through these, we would end up, we do know that we are going to have to take the magnitude of our normal vector. So this is our normal vector in terms of the parameters u and v. To find the magnitude, remember that's where we take the square root of the sum of all of these squared. So we're going to get sine to the fourth u cosine squared v plus sine to the fourth u times sine squared v, right? And then before I square the k component, I'm going to do a little bit of simplifying. So notice that when we add these two together, or we don't even have to add them together, I know that both of the terms in my k component have sine of u, cosine of u. So I can factor out sine u, cosine u. And what do I get left behind? I get cosine squared v plus sine squared v. We know that that's going to be 1 because of our Pythagorean identity, which means that the k component of our normal vector can also be written as sine of u, cosine of u. Yes, you could rewrite this using a sine double angle formula, but I don't think that's going to help us very much here. So if I just square this, I get sine squared u, cosine squared u. And at this point, there's a lot of things that I can simplify. For example, first I notice that I can factor out sine to the fourth u in my first two terms. If I factor out sine to the fourth u, what am I going to leave behind? Cosine squared v plus sine squared v, what's that equal to? 1. And then I just have sine squared u, cosine squared u. And now if I look at this, I notice that both terms have a factor of at least sine squared u. So I can factor out sine squared u. That's going to leave behind a sine squared u from this term and a cosine squared u from the second term. That's also 1. So I'm literally taking the square root of sine squared u, which is sine of u. Pretty cool. So using our trig identities, we were able to simplify this big, gross, nasty looking magnitude to something really simple. Now that we've been able to simplify the normal vector, okay, we'll continue on with finding the surface area. So the surface area, if you remember, is equal to the double integral over d of the magnitude of the normal vector, which in this case was sine of u, dA. So setting up our integrals, right? We know that Yeah, we know that u is going to range from 0 to pi and that v is going to range from 0 to 2 pi. And I know that if I replace my dA differential with these parameters, I end up with just u, yeah, du dv or dv du. Right, it doesn't matter as long as my bounds match up my differentials. So if I decide to get the annoying part out of the way and do a du first, right, then I would need the inner integral to have bounds that are values of u. And we know based on the information we were told at the beginning that u is between 0 and pi, which means that v will go from 0 to 2 pi. Now, if I evaluate this integral, remember you start from the inside, right? Integral of sine is negative cosine. So the antiderivative will be negative cosine of u, and we're going to evaluate u from 0 to pi. Then integrate with respect to v. If I plug pi in, cosine of pi, we get negative 1 times the negative gives me just 1. Right? And then if I plug 0 in, I get negative 1. So I'm basically taking the integral of 2 dv, which is going to give me 2v evaluated from v equals 0 to v equals 2 pi, giving me the answer 4 pi. And there we go. And for reference, there is actually a formula for surface area of a sphere, right? If you wanted to double check with that, it is the derivative with respect to radius of the volume of a sphere. And that's generally a thing. Your surface area is the derivative with respect to radius or some kind of side length of the volume. So 4 pi r squared gives me the surface area for this. This was a unit sphere, so the radius was 1. So verifying that we get the same answer. And they're not all problems where you can just check with a simple formula like that. If you happen to know the formulas, it's kind of cool to be able to have a method to check with, right? But generally, this is how you get those kinds of results. Being able to parameterize the surface, right? Writing out parametric equations for the surfaces that you're analyzing, finding the normal vector, taking its magnitude and integrating over D, where D, remember, is the domain of the parameters, right? Not the original variables, not x, y, z, but the parameters u and v. All right, so you essentially take a three-dimensional thing that in the past we may have used triple integrals to look at. Well, triple integrals really for volume, but basically we're able to simplify something from having 3 variables down to 2 variables. So basically the difference between this and what you learned before is now instead of having parametric equations with just t, just one parameter, you're writing your surfaces in terms of 2 parameters, u and v. And that's really the only thing that's different. And in my opinion, it actually kind of makes some of these computations a lot more intuitive and straightforward. So there we go. That is the end of this section. Happy mathing.